So we've talked recently in this chapter about how we can, without visiting the star, come to know what the star's luminosity is. Remember, luminosity is an important characteristic of a star. It's how much energy it's putting out. It's its wattage. And we also talked about how we can understand from our perspective, from where we're at, what the star's surface temperature is. That's another very important characteristic of a star. Now we need to talk about how do we know how much a star weighs? How do we know the mass of a star? And actually, we can apply this technique to understanding the mass of, for instance, a black hole as well. According to one of Newton's relationships, if we see two objects gravitationally influencing each other, or one object gravitationally influenced by the other object, then we can deduce the mass of those objects, the mass of those objects by watching the orbit, by watching the dance. And so when we can understand the mass of a star, if it is gravitationally influencing or influenced by the mass of another star, we can watch their orbital patterns. So then binary stars. So basically we're looking for a couple of stars that are near each other, close enough to each other to gravitationally influence each other. And oftentimes, if they're similar in size, they will, what we say, orbit a common center of mass. So fortunate for us, over half of the stars up there actually have what we call a companion star. And in some cases, we have a set of two or a set of, in some cases, we have a set of three or even a set of four stars that are gravitationally affecting each other, gravitationally hanging out. So when we talk about binary stars, we kind of have three different types of binary stars I'm going to talk about. We have the visual binary, where you can literally visually see that there are two stars. And then we have these two elusive binaries, where we have stars that are in pairs, a pair of stars that are gravitationally up there, but maybe they look like just one star. And in the first technique of elusive stars, eclipsing binaries, we can tell that we have two stars by looking at the light pattern. And the spectroscopic binary, we can tell we have two stars by we will see a Doppler effect or Doppler shift for spectroscopic binary stars. Now there's this other type of pairs of stars called an optical binary. And an optical binary, they just look like they're close from our vantage point, but they're really very far away. So an optical binary you could not get to the mass of these pairs of stars because they're not gravitationally influencing each other. They just kind of look like they're near each other. So starting with the visual binary, here's a pair of stars, Sirius, the dog star in Canis Major, the big dog. The brightest star in the nighttime sky actually has a companion. So we have Sirius A and Sirius B. And as it turns out, Sirius B is pretty darn dim, and it is a retired star called a white dwarf. So we have these pairs of stars up there, and we can deduce their mass by looking at their dance, their movement, how they gravitationally influence each other. So kind of from left to right, we have every 10 years how Sirius A and Sirius B would relocate in the nighttime sky. So based upon this movement then, we can, and I'm going to show you the math or the equation to use, but I just want you to generally know that this is an example of a visual binary, because we can literally see two stars, and we can use the orbital information to understand the masses of these stars. So an eclipsing binary is a little more elusive. Can you see where basically we have two stars? One is a big red star, and the other one is a smaller kind of blue star. And you can kind of see the orbital path. In this case, there's the common center of mass basically lies where the red star is. So we're going to see kind of that blue star orbit the red star. So if we're here on Earth having our little light meter, notice that we would get light from B, the blue star, and from A, the red star. So if we have our little light meter, you can see that the brightness coming from those two objects, we may not see them as two objects, but it's kind of maxed out right there. So let's go ahead and show the smaller star orbiting the larger star. Now, can you see with this position now that actually the smaller star is eclipsing? That's why they call it an eclipsing binary. The disk of the smaller star is eclipsing some of the disk of the larger star. So can you see where then we get a full value from B but a smaller value from A because part of it's eclipsed? And so actually our light meter here on Earth would go down some. Well, the star is going to continue orbiting, and we see then over here as it clears, as the little blue star clears the big disk of the brighter, or I should at least say the larger star in the middle, then we get the full value, the light from both stars. And now as the smaller blue star goes around and it continues its orbit around to the other side from our perspective of the big orange star, then can you see where now the orange star totally eclipses the light from the little blue star? So our light meter really dips down. So it's this kind of series of dips that we look for, and we can understand that we actually have a pair of stars up there. This is an example of an eclipsing binary. And then we can use that information to come up with the orbital period and then plug that in and come up with the masses of those stars. So the last type of elusive binaries are called spectroscopic binaries. And I think I mentioned they apply the Doppler effect. So can you see again, we have kind of the center of mass lies, in this case again, on the larger star A, the orange star. And we have a smaller star B that is going to go ahead and orbit A. And notice as B swings around right here, we have what we call radial motion. And that radial motion is towards us, so spectral lines coming from that star will be shifted towards the shorter end of the electromagnetic spectrum. We'll have a blue shift right there. Okay, then the star kind of swings around in front of the star B kind of swings around in front of star A, and then we have what we call proper motion. And then over here now, the B star is going away from us, and again we have radial motion, but the Doppler shift is red, so we have the red Doppler shift. Those spectral lines are shifted towards the longer end of the wavelength of colors. So this sort of kind of swinging, shifting spectral lines is indicating that we have a star up there that is moving towards us and away from us, and towards us and away from us, and towards us and away from us. And so we can again get to its orbital period. So there's Isaac Newton, and he came up with this relationship that we can plug in and get the masses. Actually, in this case, the combined mass of the two stars. I mentioned the period would be is the variable P. A here stands for the average separation of the bodies. G is a gravitational constant, and M1 and M2 would be the masses of the stars. Okay, so again, I am not going to test you over plugging numbers in per se. I just want you to know that when it comes to understanding or calculating, I guess I should say, when it comes to calculating what the mass of a star is, we can do that as long as it is gravitationally affecting or being affected by the mass of another object.